Hello and welcome back to Factorio. My name is abucnasty, and in today's video we're going to be continuing on with our Let's Design series into Uncommon Science. The goals of this video is to redesign the automation science that I created for the Megabase, and then ultimately in the end, change this out in the Megabase itself and start running a new version of this. There's three goals for the video. One is to redesign it from the ground up. I'm going to take you through the design concepts, creating it from scratch all the way from the beginning to the end. And then finally, there's going to be a test portion where we are going to run a benchmark to compare this assembly machine with the newer version that we're going to create in this video. I know that there's going to be a couple places for optimization, so we'll explore that here in a second. But finally, the end of the video, we're going to incorporate it into the Megabase and see it running in real time. So without further ado, let's get into the video. So as always, we're going to start off with a bill of materials. What are we going to need to ultimately create the science that we want, and all the intermediary steps that we have. Automation science takes two inputs. It takes copper plates. It takes iron gear wheels. Iron gear wheels are very simple to create. All we need is iron plates, and iron plates are going to come from an electric furnace. We're going to be smelting that down from ore. Specifically here, I have simulated that with these two belts. Keep things simple. Let's, for right now, just assume we have a way to create this at 240 items per second to fill a full belt. So we're going to bring these in. We're going to be smelting them down in electric furnaces and then ultimately putting them into an assembly machine to craft the gears and then go into creating the actual science. So this has come up a couple times in other videos as comments and questions, so I just want to address it here. Why am I not using a foundry? Well, a foundry can technically does have a quality version of creating the fluid that it actually needs. However, the output, even though it consumes uncommon materials here, it's not going to create a uncommon fluid. There is no concept in Factorio of that, unfortunately. So with that being said, that means that although we can actually put in the uncommon values that we want, when it comes down to the actual outputs that we're going to need, either the gears, well, that unfortunately doesn't have a selectable uncommon version because there's no intermediary items. Same thing for casting copper and casting iron. So none of those are an option for us to use for this design. You can do this if you're going to be crafting common versions of that, but the goal of this, because of the compression ratio, uncommon is just going to be better for UPS in the very end, late game, basically at the ultimate Megabase level. So we're going to be designing around that concept. So these are all the components that we're going to be using. So let's go ahead and get into the design. So to start off, let's go ahead and grab one of the basic components we're going to need, which is the assembly machine that's going to actually create the automation science packs. We're going to select the uncommon quality here, and I'm going to shove in here 4 of the legendary productivity modules, which is going to give us a productivity bonus of 100%. Then the next step here is just we're going to surround it with as many beacons as possible. So we're going to go copy this. I'm going to Control-C, copy everything, press R to rotate, and let's rotate them around until they're all the way around the entire build. So now we have a basic building block, and looking at this with rate calculator, this is going to be consuming 13, and we're going to be making 27 of them. So this is the best that we can get in terms of the number of beacons surrounding this. So what I'm going to do though now is I'm going to need a couple things. One, we're going to need an input, and we're going to be needing something that brings in that item. So let's just, for simplicity purposes, put this in here. And what is this going to be? Well, we know that this is going to require, and we'll move this down here a little bit. I would like to have a wonderful constant combinator. So this is going to require 2 inputs. We're going to need uncommon iron plates, or copper plates, sorry. And we are going to need gears that are also uncommon. So, and let's select that as 1. So I'm going to shift right click on this and shift left click on that to bring them in. This is the editor extension mod. That is what I'm using for creating these nice little purple things. So if you want to use it, that would be the mod to look at. It's created by Rhaegar, one of the developers for Factorio. I really like it, so I use it. The output then for this is going to be also coming from here. Really simple. We're just going to bring this on the belt, so it's tileable. So real quick, one thing that I'm going to touch on, one nice thing, and this doesn't actually impact your UPS itself, but kind of creating the minimum amount of undergrounds here does help with visualization. So for example, if you had, let's say, hundreds of belts all stacked up like this, and you have ore, or just, we'll just simulate this with a whole bunch of materials here. Your UPS won't be impacted by seeing a large belt like this, but your graphic rendering, especially when you're seeing hundreds and hundreds of belts, is going to start slowing down. So it doesn't make a really good experience for you if you're looking at hundreds of belts yourself. So your frames per second will drop, and ultimately your UPS will drop when you're looking at the items. But if you're not looking at it, then the game will optimize that so it doesn't show it. So it doesn't really matter, but it is recommended here to just use instead undergrounds when you're transporting materials like this. So this would be just ultimately more optimal than the setup that you have. So we're going to use that design purpose. Do you have to do this? No, but I'm going to be incorporating that into these designs going forward. So with that being said, so we have a input and output. So we have a belt here. We're going to use this and simulate that here so we can watch this happen. So the next thing that I'm going to do is I'm just going to clean this up a little bit. What I want to do is I'm trying to make this a little bit more compact. So let's bring this here, same concept. Let's have them just minimal for display purposes. Control X to move this down, Control X, move that down there. And then I'm thinking all that I want to do, and this won't really matter, but I'm just going to shift these slightly over. So what that means is we're going to have enough places anywhere around here to basically place a legendary substation. So that'll be good for when we actually make a tileable version of this. But I think that's really it. That's all we're going to need for this. So that's going to be our basic building block. And then we're going to incorporate it into creating the final output module here next. So now that we have this basic building block here, we're going to go ahead and look at rate calculator, how much we're going to need here. So per second, this is making 27. So let's keep multiplying this until we get to the magic 120 number. What is that? Well, I'll just show that here. Transport belts, it shows you how many transport belts you're filling. What we're shooting for is the number 2. That's because a half belt or a fully consumed belt would be 4 turbo transport belts if they're stacked up to 4. So 2 is kind of the number to look for, but simple number to remember is always 120 items per second. So that means we're going to need 5 of these modules. So we're going to copy this 5 times, but I'm going to want it for both sides. So we're going to have 2 different sides that we're feeding here. So let's do that. And then I'm going to copy this 5 times. So 1, 2, 3, 4, oops, and 5. So if we look at this, Alt X to bring up rate calculator and look at it, that is going to be over the 240 items per second. And this is going to be consuming 120 items total per lane. So that's fine, with this one just being slightly overclocked. So that's good. The second portion that I want to get into is now, although this is going to work, you're going to have some issues here on the final output going into this turbo underground belt, because this isn't going to be swinging all the time. So one thing that I want to do is I'm going to change this here so that we are feeding it in from the other side. That way it's never actually blocked by the belts themselves. And it can go on the other lane or the other side of the belt, so that this is always able to output and has a little bit of a buffer in the belt to basically fill in the gaps that are created when these other inserters are swinging. So what am I talking about with that? So I'm going to show this side, and then I'll show the other side as well, just for comparison purposes. So we'll put this in here. This will be our output module. And then let's go ahead and grab then again these inputs that we're going to need. So I'll move this down here. So we'll grab again a constant combinator, put that there and there. We're going to need this. By the way, press Q to select the item that you want from in here. So Q, you can do this also outside the editor. I'm going to copy that there, and then I'm going to grab these 2 from editor extensions, shift right click, shift left click, shift right, shift left. So now we have all the inputs coming in and flowing. Great. So I'm going to put this on the side here so we can watch this. And then rotate, and we'll let that run. So here for a second, let's delete this. There we go. So let's go game speed 10 just to speed it up, to remove all the buffers that are inside here. Okay. So you're seeing now these tiny little gaps that occasionally happen in the belt. And we can actually show that a little bit better. I'll show that in the debug menu here. So if you show and look up, show transport line gaps, and I press F5 now, you're gonna see that little white line. It's a good little thing that you can use. You can see the gaps that are in the transport belt. What you're seeing is this is always happening on the right side, but it's not happening on the left. And that's because this inserter, whenever it picks up, occasionally it'll run into this line that shows up here. So this little white line. And if that happens to coincide with when this is picking up, you're gonna get that little gap. So to prevent that, just use a buffering concept, emit it on the other side. This will not be the priority, as you're seeing on the top here. It's always going to pick the inside lane or the outside lane relative first because it's lower on the belt. So it'll always flow everything downstream first. But then occasionally, when this gap comes in here, it just tops it up from this side. So this is acting as a buffer now. So we're going to incorporate that now. I'm going to deselect the debug menu, and we're going to have the exact same design here on the side. So let's put that in there. And that's it. So now we have our head module, which is perfect. The next thing that I'm going to need is we're going to need to put some power in here. But before I do that, I'm going to want to incorporate something that I talked about last week with inserter clocking. So we're going to use the concept from that, and we're going to actually incorporate it here. So we're going to use the lead follower principle for this. So we're going to start off with a decider combinator. The decider combinator is going to be hooked up to the lead assembly machine. What do I mean by lead? I mean this one that is downstream of the final one. As you can see, this one's not running all the time. This is only running just to fill in the buffer because we know that it's over capacity in terms of this is higher than 120 items per second. So what we're going to do is we're going to always follow this one because this one should always be running because there should be nothing else upstream of these turbo underground belts. So we're going to connect the green wire here, and we're going to have it output, let's say maybe over here. And what we're going to do with this is we're going to read the contents of the automation science pack. So we're going to select here, read contents, and also include in crafting. And then now we have the ability to monitor this one assembly machine. So what we're going to say is, well, we have the two inputs that we know. So that's going to be gears and copper plates. So whenever the copper plates are less than 16, or we're going to want if the gears are less than 16, we're going to output an activation signal, which I'm just going to use as a check mark here. So what this is going to do now is we're going to set this up and hook this red wire here up to all of the inserters downstream. You can use red or green. I'm just using red. I like to, in general, use the principle that an input to something is green and an output or an activation signal is red, but you can't always do that. But in general, I try to follow that principle as much as I can. So for this now, all we're going to do is I'm going to select this check mark signal here. I'm going to put that in the enable, and we're going to say when this is greater than 0. So I'm going to shift right click to copy the settings, and then shift left click to apply them to all of these inserters here. And then now what you're going to see is all these are swinging at the exact same instance, but we're still having constant output up here. And that kind of makes sense because in general, these are all going to be exactly the same speed. So we can use the lead follower principle here for this. We're now going to apply the same thing, but I wanted to know that this inserter isn't constantly pulsing like this and is active. I'm going to go back real quick to the original design that we had to showcase that. You're seeing here that these are constantly flickering. That is one improvement that I want to make by using the new lead follower clocking method to expand upon this, rather than just reading the inputs and when it happens to need something. So we're going to do the same thing now for the output. So again, we're going to grab a decider combinator. We're going to read the contents again from the assembly machine, but this time what we're going to do is we're going to say whenever the automation science pack is greater than 16, I'm going to output again an activation signal, so check. And I'm going to bring that now with a green wire, and I'll explain why I'm doing it with green over red and breaking the rule that I had in a second. But now we can basically just copy the same settings. So this is here going to be a check mark. And we're going to say just when this is greater than 0. We're going to shift right click, copy them to all of them, and go from there. So what we're seeing now, compared to the right-hand side, is that all these inserters are now swinging at the exact same time, and they're always grabbing exactly 16 items every single time they swing. So that's already a nice improvement that we've made to limit the amount of time these inserters are considered active. So I'm going to go ahead and copy all these settings other than the actual two, what are these called? Forgive me, the decider combinators. And I'm going to bring them over to the right-hand side. So let's copy it, press H to flip it. Why can't I? There we go. And we will shift left click to paste it. So now all these are disabled because we have to connect them all up. So we're going to do that here. I'm going to ultimately want to create this as a mirrored copy because we know that for this, no, I think this is going to be fine. We do need to figure out how to get these signals over to the other side. So the easiest way we can do that is let's figure out the power next because we can run electrical wires over that. So for this design here, I'm going to want to incorporate a place for this power to go. So let's choose a side, and the convenience part about this is that this is going to be exactly the amount of room that we need to power everything on both sides if we place it here, the substation. So I'm going to place this here, and I'm going to say I'm going to place this also down here onto the next one. So let's see where the next location would be. So we can't get away with that, so let's go ahead and put that there. And then we're going to need one more to activate this, so we can probably put that, that's fine. We'll put it right there. So now we have power going along everything, but now we can also bring a wire and attach it to this at some point to bridge the gap. So for these green wires, this is straightforward. I'm going to place this in here, so this is connected. Now for the red wire here, I'm going to want this connected as well to send it across to the other side. So I'm going to connect this here, and then that's going to give me enough room to get over to the other side. So now we have one assembler reading both sides and outputting just when they happen to be low or when the science is high enough. So right now you're seeing some gaps, and that will adjust in a second once these have stabilized. So this will take a little bit to happen, but once this all stabilizes, now all these are swinging at the same time and all the buffers are the same in all the assembly machines. So there we go. They were outputting exactly 240 per second. The nice thing is that these little gaps in the lines they're seeing by having the debug menu open, those are syncing up now. So, all right, so we've designed now this head module. This seems to be in a good spot. Next, we're going to focus on getting into crafting the materials that we're going to need. So we're going to need gears, and we're going to need copper plates. And we're going to get into that next. So off camera, I reworked this a little bit. I realized that with the previous design that we had, we were running 2 full lanes here. And the original reason for why we had done this was that if you're consuming, one side is really only consuming 120 items per second, so a half belt. So using this kind of concept here where we're side loading both the belts with a turbo splitter belt, we can make 240 items in furnaces and output then also gears from the side. And so we could be using the full assembly of 100 or 120 items per side by just making one. And I want to do that because ultimately the gear, the crafting recipe here, we can fit enough beacons around this to make 240 items per second. So instead of having effectively one extra assembler per side, we're going to go ahead and just take this concept and I want to craft this next part with just using one assembly machine. So in order to do that here, what we have is I am crafted this little assembly here to showcase that we're going to be outputting on both sides and we're flipping it in this way. And the intention that I have right now is I could probably put right in here a gear assembly line that could output, in theory, something that is going to go this way and this way. And I'd ultimately like then materials to come in here to feed it with the iron plate. So I know ratio-wise this is 1:1, so in order to make 240 items per second, we're going to need, well, let's say if I can do math here, that's close enough. So we're going to need 240 items as the input and 240 to get 240 items on the output, and that's going to feed both half lanes of both assembly machines. So before I get into the actual designing of the gear assembly line, I wanted to touch on a couple things. So the nice thing too here is that by unifying both of these banks together, we can remove a couple other decider combinators. So before, I used to have one on both sides and feed, like we just showed, the 1/2 bank here that's making 240 items per second. But by combining this now as one assembly, I can use one decider combinator to monitor this furnace as the inputs, as the lead, and then I can use this one as an output as the lead. In theory, these should all be unified, and what I want, I'm trying to avoid balancers as much as I can, but in general, these should all be consumed at the same amount, because these are ultimately going to be belted all the way back to the labs from just using belts. So this shouldn't be an issue of them monitoring either side, but we'll test that out later. But in theory, this is good because this is going to eliminate one extra combinator, and then all of these inserters are all controlled off of just these two assembly machines. So with that being said, we're going to go ahead and get into gear production. So like stated previously, we know that for gear production, we're going to want some things that are going to output to the sides so that I can feed these in here. It's ultimately where the intention is. So we're going to kind of keep that in mind, but first I want to figure out the inputs. So in a previous video, we designed already our lead follow furnaces. So I'm going to use, there's two different flavors that I can use for iron plates. If I'm space constrained, which I'm not, I could use this mini version. This is the fully beaconed version that I've already tested out to be the most performant UPS wise. So we're going to use that as our base template. The kind of convenient part, and this was also intentional with the exact placement of these substations, is that now these are going to line up exactly. So if I look at the menu here, these lines are all going to line up. So this is just, again, I'm a fan of symmetry. So it's convenient that all these things are lining up perfectly. And also it's functional because they're going to provide enough power to everything here. So I know this is going to be the raw inputs that we're going to use. So let's use this here. And I'm going to copy this over and place this just somewhere up here. So I'm going to want inputs. So let's go back out of the menu and go back into the editor. So I'm going to bring in a single belt. I know I just need a full belt to be consumed here because this is going to, once this kicks off fully and starts running, this is going to consume under 240, but over 120, so we need a full lane. So this is going to output here. Again, this is using that buffering concept that we talked about before for automation science, and the assemblers there to put on both sides of the belt so that this can, because this is actually over 120, so that is convenient then to just keep these always running and fully saturating the belt. So it's not making 240, but it's over that, so we use both sides. So then what I'm thinking here is I want to design this in such a way that I can bring the materials in. So since this is 240, you need at least 2 legendary stack inserters to fully bring 120 items at least off of a belt. So I'm going to have that, and I'm thinking that what I'm going to do with this is I kind of want to sneak this in. So let's bring this a little bit closer, I'm thinking here. So, yeah. So we're going to bring this a little bit closer so that these beacons are all impacting it. And then I'm going to take this and bring this in. So there we go. Do the same thing on the other side. So then that will be the inputs to the assembly machine. Then on the outputs, how do I want to do this? So let's go ahead and fully beacon this. And we could place this here, and there. So now this is fully beaconed. This is making over 240, which is great. But, all right, these beacons are going to be a problem. I can't exactly, I can't output from this side, so that's a no bueno. So we're going to move this up 1, and that will work. So then what I can do here, all right, now I can output from here and here, but I need 2 more. If I put something here, this is going to become a problem. So what I'll do instead, let's delete all this stuff. I'm going to rotate this in. I'll take these on the outputs. And then I want to bring this out. Oh, the easiest option is just this. Great. Okay. So I like that. Let's copy that on the other side. There we go. Then that's going to output it. I don't really care about them being on the same side of the belt. That doesn't really matter because we're ultimately going to be feeding it into here, and the splitter is going to take care of it, feeding it to both sides. So that's also nice. It unconstrains the inserters and just allows them to freely output as fast as possible onto this belt. So let's see. I think this will work out also spacing wise. So let's copy this and let's move this in as close as I possibly can. And then we are going to go ahead and just feed this in here. And feed that out there. I'm considering one thing that we could try. I'll create two versions of this. I don't know if it's quite worth clocking these inserters. We could do it by reading just the contents in here and having them just swing when it gets lower than the desired amount that we have. So we don't need it constantly running. Because right now you're seeing that these are active all the time, and I think that makes sense. I don't think there's going to be a huge benefit to optimizing this because these inserters do need to swing constantly to keep up with the demand of this iron gear assembler. So although we could clock it, they do need to run constantly when this entire assembly machine is crafting, unlike these that only require ever occasionally. So I'm going to leave it off. I don't think there's going to be a benefit, but I'll create a version that's clocked as well, and we can compare them and see if there's any UPS benefit to it. My assumption, though, is it's not, because this should be running constantly to fully consume everything. And we can test that real quick here. Let's delete these up here, and just for noise, I'm going to remove the gaps in the transport lines so that we can monitor this. We'll let everything completely consume and back up. So now everything's saturated. At this point, I'm going to go ahead and add back up here the outputs so that we simulate it being consumed, and let's run it as fast as possible for a second. And then we're going to bring it back to base speed. So I can press F5 to see if they are stopping. So it seems like they do occasionally stop on their own. So this might benefit from clocking. We can try it out. So I'll keep it like this for the first version, and then we'll iterate from there. So next, what we're going to need to do is copper plates. So for copper plates, we can use this same design. Again, we have these blueprints are listed in the other video that I'll attach in the video description. But we have now the ability to use the same design here, but for copper. So what's kind of convenient is because these are the same footprint, my thought here is I'm going to delete this input that I have. I could move this so that they are on both sides respectively. So if I copy this here, let's just move this over here just for convenience. If I copy this, I can place this exactly here on the side, because we only need a half lane, and that's what this is going to do. So that's perfect. And I can also put it on the other side here. So this would technically need on both sides a clock, so we could synchronize it. So we'll try to see if I can route these wires over. I don't necessarily like it. I don't like that I have an extra decider combinator on both sides, but it is going to be needed in order for controlling all of these on the sides here. But we'll experiment with that. Let's just use this as a reference point. So I'm going to just input here the raw materials, just so we can have this running. And then I'll think of a better way to do this, because ultimately what I really want is I kind of would like this to be the input here and have this on the side, and then just split between the two, because that way it's really clear for anyone that's using this, even outside of me, that you don't need a full belt here, because we don't need that here without the explanation. So we only need half a lane, so this is perfectly fine if we split it in this manner. So we'll redesign that. But let's just feed this into here. So I'm going to bring this over and in, over, and then in. And then we can just for optimizing the render graphics, we can bring this all the way over. So let's just bring this all the way over here. So that seems to be just fine. And this is already clocked, or using the lead follower concept. So what I could do, I'm trying to think of a way that I can easily bring these wires over, because I'd like this to be connected to this one and vice versa. This is already using green wires for these inputs. In theory, these are all smelting at the same speed and should consume everything downstream here at the same speed. So I wonder if we can use the lead follower concept, but still, because we have greens here, let's try this. Let's try deleting this completely. And let's try bringing this green wire over and slapping it into this furnace here. This is an interesting thing that I want to try, because what this does, and what's convenient about this, this is exactly the issue that I was concerned about, is that this would block up. Or nope, I still need red wires to come across. That's my bad. So let's bring this over here, and let's get that over there, and let's bring the output here and connect that there. Will this auto-correct itself once things start getting consumed downstream? What I'm concerned about is that I'm inherently building a dependency between copper and the iron plates. So in theory, once this starts really running and the gears are consumed, since it's a 1-to-1 ratio here and all of these have the exact same ratio, this should be fine in having one furnace controlling all the inserters here. So let's let this run for a little bit and see if this will correct itself. Let's go ahead and just speed this up. Well, that seems to be just fine, because we're clocking everything up here, everything down here. Nice. Okay, well that's kind of a cool thing that we just need one input monitoring this. Again, this works because this is the same speed as this one is. So, in essence, now all the inserters are swinging at the same time, all have the same outputs, and now we've synchronized them for a full lead follower concept. Awesome. All right. I'm going to work on cleaning this up, and I'll come back in a second once I've done that. So I've redesigned the inputs now to feed just the 2 inputs here, just to make it obvious that we just need a couple of inputs and that's it. So this is going to feed in here, again, just using a turbo splitter so that it's not going to both sides of the belt, but just is consistently going just to the outside lane on both sides. I'm just doing that so they're constantly stacking up. So like explained in the last video, you do want back pressure on the line, and you may not really fully have that if we remove that. So just to demonstrate that here, if I run this constantly, all this is really going to do is just buffer this. You know what? I take that back. I'm going to keep it just like this, just to make it simple, so that these, having the extra buffer there isn't an issue. And it removes one extra splitter, so one extra component from the whole assembly. So, cool. Take back what I said. We're just going to keep it this way. So it's still back pressured no matter what. It just takes a little bit longer for it to fully saturate the belt. By that, I mean in practice, when you're running this for hundreds of hours, it doesn't matter. But for the micro startup, that just means that the very first time you place it down, it takes a little bit longer for everything to sync up. But that's also fine. Okay. So now we have, delete this to clean this up. We have a basic assembly machine that is going to be making all of the items that we have needed all the way back. So I'll touch base on the raw inputs here now for a second. So I'm going to want to have, I'm going to go into the editor here just to simulate this. If I'm going to go here to resources, I'm going to create a brush for copper. So let's put copper somewhere. I don't need a whole bunch of it. Let's put it somewhere over here. That's good. And I'm going to put some iron over here. Perfect. And then I have some blueprints. I'll share them just so that people can see them. I'm going to finalize them. So I'm actually thinking I'll wait. This upcoming week, I'll do a deep dive into uncommon ore miners and upcycling for that. So stay tuned for that and subscribe if you're interested in seeing it. So I'll share these at that point. So for right now, just take this with a grain of salt. What these do is this is a blueprint so that I can place down one of these miners here. And I have to then select the type of material. So in this case, it's iron ore. And all this does is it just has filtered slots for all the different materials that are inside here. And you're going to see that these assembly machines, or rather the recyclers, are going to destroy all the common or basically any material that isn't uncommon. And then the uncommon is going to be taken out of this cargo wagon and placed onto this belt. So this works right now anywhere above like mining productivity 2700 that you can use this particular setup. So I will post some other video in the upcoming video. I'm going to showcase a couple other designs that you can use that are going to be for earlier game, but you can use that. I have found, and I may need to refine this, is why I'm not sharing it quite yet. These can get stuck, so at least on the very first time they start without being fully run. So sometimes when I place it down, I have to delete it and then restart it. So we're going to copy the same thing down on the other side for copper. Just monitor that doesn't get stuck. Good. So that is the entirety of what we're going to need to make Uncommon Science. So this is comparing this against the original build. This is going to be here. We'll copy this. So it's a much larger footprint, but I don't really care about that because we have like almost virtually unlimited space. But this is using a lot less components than the original design. So just per stack here, this had 24 assembly machines. And in the new design for creating this has now only 20. So we've removed 4 extra assembly machines. So basically all these 4 on the top, which is nice. So that's a nice change there. The furnaces, the quantities are the same, but they should be running in theory less often, which you can monitor here by pressing F5. So you should see these stopping and starting, which is good. So the only thing left to do is to take this design that we have. I would like to create a clocked version as well and compare the clocked version. I'm also going to include in this benchmark, I want to include these big mining drills so that we have that as well, so that we can compare the full consumption of running the full setup, not simulating the ore inputs. And then we're going to benchmark that. So this design, one that has a clocked version of this and one that doesn't, and then finally compare that against the old one. Just out of my own curiosity, I've created 2 additional new types of builds. This one here is using just traditional inserters, just pulling off the belt and relying on wake lists. I went in depth on that on the previous video that I posted. If you're more interested in that, go check that out. Otherwise, on here, this second one is going to be using the thresholding concept, where it's going to be just pulling items off based on a condition. And finally, the third one here is going to be using clocking, where on a very fixed interval, so from 0 to 13 ticks, the clock will, for 0 to 4 ticks, be enabling the inserters. So we are seeing little rest periods here. Here we're seeing also rest periods as well, just based on the thresholding, whereas here this is being considered active all the time, but then with short little pauses. So I don't think it's going to make a big difference, because it's just one assembly machine, but I thought, what the heck, why not just try it anyway? Since I didn't cover this in the last video, this is a test bench setup. I'm going to actually go through setting up the test bench file. So I have a base version that I've created here, which is just a test sandbox. You can do that pretty easily, and I'll save this here for now as I've been working on this. So I'll just call this V3. I'm going to exit. I'm going to go and create a new single player, new game. If you're using already the editor extensions testing, like the mod, so this is a mod here. We go to mods. The version that I have here is called editor extensions. Again, it's by Rayguard. So once you have that enabled, it opens up here the ability pretty easily just go and create already a mod scenario. So in this mod scenario, this is just exactly that test bench file. I modified it slightly just so I'm always in the same location and changed some of the mining productivity levels for myself. But This initializes, you're then in a world that is already set up just to be in a test bench world. You can recreate this yourself, but by just going into the vanilla new map and going into the editor, so you can type in /editor. And you can go into the surfaces and you can fill everything with lab tiles. You can basically set or change any of the map generation settings that you have here. So those are things you can mess with if you want to, and that is the way that I have been using this to set up the test benches. So once you're in this menu, you can press T to go to research, and if you have the editor enabled, you can press Shift and then T to research the things you want. In my case, I'm setting this to a very specific mining productivity level, so you can enter this command. This exists on the wiki for what you need, but you can just basically copy this and set this to whatever level you want. So in my case, I'm just going to go with what my mega base currently has, which is 8,000. And then when I go here to the technology tree, I can see that's 8,000. Again, you can press Shift T to increase the research you need to get to. So I've already done that. So let's go back to the world that we had. And I'm going to go and walk through actually setting up the test itself. So in here, the goal that I have is I'm going to go through the 3 different builds that we've just created. I'm going to set up the original one first. So this is the current one that's running in the base. So we're going to set this one up. I will put it, I don't know, somewhere. That looks good. So I'm going to need to feed these inputs. So what I'm going to do is I'm going to go to the resources tab here. I'm going to go to brush. I'm going to set the size to something that makes sense to me. I need copper ore, so let's just put this, I don't know, somewhere like this. Press it a couple times just so we have a good amount of that resource. And I'm going to move over here, and I'm going to build the same thing over here. 1, 2, 3, cool. Good, enough. This won't run out anytime soon with the test bench. So I'm going to go then to the uncommon modules. I'm going to select my miner that I have that works again at a very high mining productivity level. So then what I'm going to do is I'm going to stamp this down, and I'm going to select copper ore. Going to do the same thing over here, and select iron ore. Then I just have to route these in. There we go. Just speed up the game real quick. So this completely fills all the way out. All right, great. And then what I'm going to do is I'm going to grab from the infinity loader here, so we have a constant output. And there we go. Perfect. So now we have a setup here. I'll trim this a little bit just because we don't need this many resources basically by right clicking and then selecting the resource and killing it. And yeah, this looks good. So there's a second mod that I have for region cloner. This makes it super easy just to copy and paste everything, including the resources that are underneath it. So we're gonna go ahead and select that and get the selection tool. And I'm going to go down here. This should be the full width of this thing, so I'll just grab somewhere like that. It looks good. So I'll select this whole thing, and then the number of copies we're going to do, let's try 12 first and see what that looks like. Before I do this, I'm going to go ahead and save this, just because it's a pain to undo it once you run it. So we're going to say 12. So if I copy this 12 times, that'll be 960 times 12. Or total. So then whenever we go and create the other build, we'll have to do it to 24 times. So I'll go ahead and press start. Alrighty. So we've copied this now. Looks like total number of times. So perfect. There's 24 of these. I'll zoom over. Great. Let's see what we get when I run this at 100. Just kind of what our UPS is kind of at. Okay. It's 1100. It's pretty good. That's probably good enough for the benchmark. We could increase it more and have more of these builds. Don't have necessarily an issue with that. Let's go ahead and just do that. We'll just add some more. There were some comments that I got in the last video talking about that they wanted to see just increasing the total number of entities. I don't think it's going to make a difference, but I'm going to go ahead and just try it out for this video. So let's select everything here again. And we are going to go to number of copies. Let's go with, I don't know, let's just go ahead and do 24 of them. So just a lot of them. Fantastic. So now this is all the way over here. Great. So let's try running this again at 100x speed. All right, now we're way lower frames per second. This is kind of where I'm getting at. Like, I don't think it matters if you're at 600 UPS or 1200 UPS, because the base game, just when I'm running this editor, it's like at 6000 UPS I'm running if there's no entities in it. So I don't think it makes a difference if the gain value is at 600 versus 1200. So we'll try this time with this number. So just for us to keep in mind, we're gonna have to make 48 copies of that. And so we're just gonna have an absolutely ludicrous amount of uncommon automation science packs at 1.4 million per minute. So this is just very, very high number. That's totally fine. So we just got to make sure on the next builds that we're making 1.4 million for all of those as well. So I'm going to go ahead and save this. I'm going to call this Red Science 960. All right, so I just ran the benchmarks here. Before you look away, because this is code, I just want to quickly go over this in case you missed the last video. This is just a PowerShell script that I created. All that it does is it's going to launch Factorio in a headless mode. So that means there's no user interface. And I've just created a semantic link to the Steam version of Factorio, because that's what I have installed here on my machine. And then all this is going to do is, it's just to make this simple, it's going to launch factorio.exe, so the executable itself. It's then going to take, here in this folder, I have all 4 of those saved map files, and it's going to include that here. So it's just a list of these 4 that it found through just some console commands here. Cool, we have these zip files. It's going to point Factorio to launch and execute each of these. And then it's going to benchmark for a number of ticks. So in this case, it is going to be, I've specified here, this is going to be 7,200 ticks, so 2 real game minutes. These are running at 100x speed, or as fast as they possibly can, so it's not, so this shouldn't take actually 2 real game minute or real minutes to run, but that's simulating 2 game minutes. And then just have a parameter here to specify it that we want to execute it 5 times, so that you're seeing here. So run number 2 of 5 of this map. We see it again here and then again here. So that's all that this script does. It then at the end, whenever this benchmark finishes, it's going to output all the entire executables, like the logs that are coming out, just like you can see logs here. It's going to put it into a temporary file, and then we're going to go and extract some values from the final text output that comes out. So the fancier word for that would be a string. So we're going to take that string of text output, and we're going to go and do some things to manipulate it so that we can get the execution time, start time, and then eventually just calculate the effective UPS. So it takes that, puts that into a CSV file, which is here. So here's all the test results. And then I've gone ahead and put this into a nice, pretty document so that we can talk about it easily together. So this is Markdown is the format for this, so that we can just very easily go and just open the preview and render it separately. So going to show that now here. This is going to be a link included below is to my GitHub repo where you can see this yourself. And if you want to run the test benchmarks against your own CPU, you are more than welcome to do so. You can just open this up and point your terminal to this particular folder and then just execute the benchmark yourself. So no other dependencies are required. So pretty simple. You may just have to change it so that it looks at a different version of Factorio in case you don't have it installed via Steam, but if you do, it should just work out of the box. So where are we at? I've summarized here the different automation science builds. So I'm calling V3 the one that we just built in this video, and V2 is the version that I'm currently using in my base. So we've documented how much science we're producing and a little bit of the terminology. So again, threshold is for the control strategy that we're using to control the throttling on the gear assembly machine. So what's interesting here, just diving into this, is the threshold versus clock strategy didn't make a big difference. They're almost exactly identical, which I kind of expected. You really start to gain and see the benefits of clocking or thresholding when there's more and more inserters that are being used. So that lead follower concept that we talked about in the last video, that was the bigger difference that we're going to be seeing here compared to the threshold only version that we were using before. We also use a lot more beacons in this design, so it should just be better anyway, even if we don't care about the inserter control strategy. But so what does this really mean? This means that overall threshold or clocked doesn't matter, but it is slightly better. I'm almost borderline calling this noise at this point, the difference here between these two designs, but we'll document it because these were almost identical across the runs. So it seems like there is some variance, but not a lot. So looking at this then, if we're going to declare a winner, I'm going to call it either the threshold or clocked version. I'm just going to personally use the threshold version because rounding wise, it was slightly better, but it's just an easier control strategy than clocked. So I'm just going to keep that since they're both effectively the same. I'll remove a couple additional logic that was there just to have an actual clock. So it makes it just a little bit simpler. So I'll take that. So this is slightly misleading to just look at this number. So the percent differences that I've calculated here, this is going to make it a little bit clearer for us to talk about. So the actual comparability between the new V3 versus the V2, that is what we're calculating. So what's the percent difference from the current one running in my base? So that's here. That is it was an 8% increase from the thresholded version. Again, really close, 7.99%. For the clocked version, and then the unclocked version of the assembly machine making gears was slightly behind. So kind of makes sense. Those are running all the time, so giving them the slight ability to pause for 2 minutes is good. Since Red Science is running all the time, I'm just going to go with whatever is going to tell me is the better result. So we're just going to go with threshold. So overall, and I need to update this. This is inaccurate. This was the better percentage, which was 8%. So this is a percent increase that I've calculated here. I'll update that before we go, before I publish this, but that's basically it. So that's the conclusions of the testing results. So we've made a definite improvement. There'll be a link to the blueprints below if you're interested in using it. And I'm going to go put it now into my base. All right, so we're back now at the Mega Base. We've shipped it to production, yay! So here's that same design now implemented in the real world. I added a couple things. I realized I forgot to add some roboports on the last design, so oops, if I didn't have those, then it couldn't build it. The bots all came out and then got stuck, and I went, oh yeah, I kind of need roboports. So I've added them back in. We're producing now all 8 lanes here. And it took us a little bit to ramp back up to the full production amount just because Red Science is constantly being used and I don't really have a lot of buffers other than the belt itself. It's only a buffer of about 430,000 or so, so I had to slightly tune the numbers over here just to reflect that. So we are keeping the full belt when it's fully saturated should be about 439,000. So that's the target amount. So we're back to 100%. So coming back here, all of them are now implemented. There's a slight amount of extra space that was used now that occupies this, but I don't care. It's not like we're really limited on space here, so not really an issue. So those belts come down, feed back into the main assembly, or not assembly system, but you know, the main science hub. So we're back now here, fully consuming Red Science again, and yeah, back at 4.4 million. So if you've made it this far in the video, thank you so much for watching. I really appreciate all the comments that I've been getting and feedbacks and suggestions, and I'm trying to iterate on top of that. My goal for the next upcoming weeks is to do at least per week a science. So next week is going to be green science, followed by blue science, etc. I will occasionally put something on maybe Thursdays or Wednesdays where I'll do something like I did this last week with inserter clocking and concepts around that. So stay tuned and subscribe if you want to see more content similar to that. Otherwise, my name is abucnasty. Thank you so much for watching. Have a fantastic day.